Okay, so the problem number 9 first is that we need to construct a counterexample to disprove the following generator G prime is not a pseudo-random generator. Okay, let's see what G prime is. G prime is taking an input CDS, and it is based on another pseudo-random generator G, okay, which takes S and S+1 as inputs. Okay, the first call is using G of S and the second call is using G of S+1. So let's visualize this a little bit. So G takes an n-bit number, binary number, and maps it to a 2 n-bit number. So you feed in an n-bit number, you get back a 2 n-bit number. G itself is considered a secure pseudo-random generator. Okay, in our lecture, whenever we say pseudo-random generator, we usually mean cryptographically secure pseudo-random generator. So I will not keep saying that. This G of S is usually a garbage, okay, meaning it's not easy to predict what the output of G of S is, unless you know S, of course. Okay, what is G prime? G prime is basically taking an n-bit number and going to give us 4 n-bit number, right? Because it's calling G under the hood 2 times. This is 2n and this is another 2n, and we are putting them together, so it's concatenation. So we should get a string of length 4n, right? So our goal is to come up with a counterexample to show that this is not a good pseudo-random generator. It's interesting that this piece is a pseudo-random generator, right? This piece is a pseudo-random generator, and this is also a pseudo-random generator. But if you put them together, they may not be a pseudo-random generator. That's interesting. Okay, how do we come up with an example? If somebody gives us just a G prime of some number S, we don't know S, okay? They're giving us G prime of S. What will be the length of this? This is going to be a 4n-bit number. We cannot immediately tell whether this is coming from G prime of S or coming from a truly random space of all 4n-bit strings. We cannot tell easily. So we need to come up with other ways to do this analysis. What if we allow the attacker to query G prime of 0, for example, and G prime of 1? Okay? Now things become very interesting. G prime of 0 is nothing but G of 0 concatenated with G of 1. Okay, what about G prime of 1 is nothing but G of 1 concatenated with G of 2. So now we can come up with an idea of distinguisher, right? To distinguish between truly random versus pseudo-random. Okay. If we were interacting with a truly random generator, right? If we are asking for the G prime of 0 to a truly random generator and also asking for G prime of 1, we expect these two outputs significantly different from each other, meaning you don't really have a polynomial way of, you don't have a polynomial time distinguishing algorithm that can tell whether, you know, G prime of 0 and the G prime of 1 is coming from a pseudo-random generator or from a real random generator. However, if we are interacting with a pseudo-random generator, all we have to do is look at the least 2n bits, right? Here are the least 2n bits of G prime of 0. And we look at the most significant 2n bits of G prime of 1, which is this portion. If they are equal, we can conclude that our G prime is pseudo-random generator, meaning we are interacting with a generator that's not truly random, okay? Which is not good. In cryptography, we should not be allowing the attacker to distinguish between a pseudo-random generator and a real random generator. But if G prime is treated as a pseudo-random generator, they can distinguish. If they can query the generator G prime at different points, say 0 and 1, or they somehow manage to obtain a copy of G prime of 0 and the G prime of 1, then they can tell about G prime, okay? So in a truly random scenario, this can also happen, but what is the probability this can happen? So remember, this is 2n bit, this is another 2n bit. So the probability that the least significant 2n bit is equal to the most significant 2n bit of another number is 1 over 2 power 2n, right? Because we're talking about equality of two 2n bit strings. This is 2n bit, this is 2n bit. So what is the probability that two 2n bits are equal? Is 1 over 2 power 2n, which is very, very negligible if n is large. Okay, this is basically it. So to summarize the long story short, this generator is not a secure generator, secure pseudorandom generator, because if we get to know g prime of 0 and g prime of 1, for example, or anything like this, where we can compare the least significant bit of 1 against the most significant of another one, we can confirm immediately that with high confidence that we are interacting with a weak random number generator. Okay. Therefore, this is not good for cryptographic purposes. All right.